So last time we were introducing a concept which is defining a rotation matrix once we have as data an axis, a generic axis, a unitary axis, around which we want to rotate by an angle generic theta. Positive is if it's counterclockwise, when the viewer is oriented like the unit vector with the head on the arrow, otherwise negative. We have introduced at the end of the lecture some notation that we will use, and you will recognize here that we have spent some time in defining an alternative notation for the vector product. I just remind you this passage. When we have a product n vector S, we rewrite it as a skew-symmetric matrix capital S built with the components of the first vector multiplied by the second vector, and we obtain the resulting R vector. There are other notation that we need in the right after this slide, and then we move back to the treatment of the axis angle method. In particular, consider the matrix C, exactly that matrix on top. And consider the product C times, C transpose times C. Remember that C, which is some rotation matrices that we still need to define, which has only one column defined as the R vector given by the problem. So we can rewrite this product as follows: N transpose S transpose R transpose times NS R. What is the result of this product? This is a rotation matrix, and this is its transpose. So it's the identity, because the transpose is the inverse of this matrix, so we know for sure that this will be the identity. Now let's perform actually a computation. How do we multiply two matrices having the same number of column and rows in order to have the consistency? We do the product row by column, and so on. And this is the easy way, because I have the first row and I have a name for it, N transpose. So when I multiply the first row by the first column, I get the first element here on top, which is nothing else than N transpose N. Okay? Now, this second element will be the product of the first row times the second column. But these are orthogonal vectors, so N transpose times S will be 0. Okay, so I have a 0 here. Similarly, N transpose R will be 0. Now, second row times first column, same story. S is orthogonal to N because they are two vectors of a rotational matrices, so two columns of the rotational matrix, so this is 0. Then S transpose times S and S transpose times R will be 0, and without difficulty we can complete this. And now we recognize that since the column of a rotation matrix are unit vectors, so this is nothing else than the square norm of the vector, so it's 1. So this is a 1, a 1, a 1, and we got the identity. Okay? Now, let's make things more complex. Have this product. What is the result of this product? don't look at this. C times C transpose, with C being a rotation matrix. Again, the identity. Okay, so this will be equal to the identity. But now we have a problem. Why we have a problem? Because we cannot say how to organize computation. Here we have columns defined. Here we have rows. So it's exactly the opposite of this. Of course, we know the result, but we would like to have an expression here, because this expression will be needed in the following. So with this in mind, consider now a generic product of two matrices. Now, this is a special case, A times B. But since we want to make things more complicated, let's put a third matrix in between. And the third matrix will be given by a matrix which has all zeros except a 1 here in position row I, column J. Okay? And now let's perform this computation. So this will be A times, and now let's do the product of this elementary matrix. There's only a 1 somewhere, all zeros, times the generic B matrix. So I think that the first row will be 0 times any column of B will be 0, and so on, until we get to the ith row. And the ith row will be 0, 0, 0, 1 on position J, and then other zeros. So when multiplied by the columns, it will select only the jth components of each column. So we can write here at position I, remember that this is position I, there will be some row of B which will denote as B transpose J, because it's the jth row, because the 1 is in column J. Okay? And then 0. Okay? And now let's do the product A times this. And now I will start with the first row of A. We'll multiply the first column. But I see that out of J, the only, out of the element of the first row of A, the only that matters is the one in position I, because this is the ith row. All zeros will delete the content. And this is true for the first row, and then for the second row, only the ith element will matter of matrix I. So as a result, I will have this kind of final results. And pay attention, this is a column, and this is a row. So this is a matrix, and in fact it's the outer product of two vectors. And if things are consistent, this is a matrix itself. Okay? Everything is clear here, how I do this computation? Now what happens is if I have here a factor alpha instead of 1? Well, nothing matters. I will have a factor alpha here. What if instead of having just an alpha in position ij, I have also a beta here in position row h, column k? Well, I split the problem in two, and I repeat the same thing, only with different indices. So I will have plus beta a h b k transpose. So the sum of this matrix plus this matrix, each with its own coefficients. Okay? Now, if we put all together, we can now cancel this part here on top, because this was the easy part, and make some conclusions. Namely, if I have a product of two matrices, and in our case will be CC transpose, okay, so one the transpose of the other, and in particular both rotation matrix, so orthonormal matrices, I can imagine that in between it's like having A times the identity times B, correct? But the identity is one of this matrix of this kind, is a matrix which has one only in position 1, 1, 2, 2, 3, 3, H, H, and N. So it's the sum of product of this form multiplied by 1. So this is just the sum from E to N, if those are square matrices N by N, of AI transpose, B I transpose. Okay, this is also called the sum of DIAGs which means that we can rewrite the product of two matrices as the sum of outer products of the columns of the first matrix times the rows of the second matrix. Each product is a matrix, so this is a sum of n matrices. Okay? Now we have a special case. Let's do this. A, any matrix. Suppose that we rewrite it as A times identity, which is again correct. And now we treat the identity matrix as the matrix B, so its columns will be elementary columns 0, 0, 0, 1 in position I, 0, for I that goes from 1 to n. So using this, I can write any matrix as the sum of each column multiplied by some rows, and the Aith rows is 0, 0, 1 in position I, 0, 0. And this is the so-called dyadic expansion of matrix A. Okay? So what this formula says, it seems complicated, but it's very useful when you have to work with product of matrices, you know only parts and so on and so on, which means that the generic matrix can be built up as the sum of n matrices. Each has the column of the matrix A in the right position, and everything else is 0. So you're summing n matrices, each of which have only a non-zero column, exactly the column in position I, and then this moves through the matrix. It seems more complex than just writing this, but this will have some use. Okay, so we have all formulas here, and now we go back to this product, and what do we have? It's like having the identity in between, so this is n transpose plus s transpose plus r transpose, and this sum of three matrices, each of which is the outer product of one of the columns of the rotation matrix, gives the identity. Okay? Good. I think we have everything we need. Yes. So we can proceed in our arguments here. So again, we need to rotate. Actually, the slide that you needed to see was this one. This was our problem. So given a unit vector r and an angle theta, we would like to, which makes the word rotate around this axis, we want to find the rotation matrices expressed only in terms of the data of the problem, so the unit vector r and the angle theta, that describe the rotation on vectors, or the change of orientation of things, or the change of coordinate if we consider a vector in one frame with respect to the original frame which is not rotated. The three interpretations that we have given. So this problem is solved as follows. We build the unknown matrix, which we called R as a function of the data, theta and small vector r, as the product of three rotation matrices. The first rotation matrix is this unknown matrix C, which will move the zeta 0 axis, will bring this on top of the R vector. Okay, so I have the original frame, I have a generic R vector here. I will rotate things so that my zeta 0 is aligned with R. What is this rotation matrix? I don't know. It will have two columns, but I know the third column. Why? Because the column, the third column of a rotation matrix express the directional cosine of the new z-axis with respect to the original one. The new z-axis is the vector r that was given, the unit vector r, so I know that the third column of this matrix is r. I don't know yet how n and s are made, but we will see that. I don't need to know this. Okay? Now, once after this rotation, I have my z-axis on the original unit vector r. So, if I do a rotation of an angle theta around this axis, I will make an elementary rotation around the current z-axis. And I know already what is the structure of this elementary rotation matrix. It's something that we have called Rz of theta, and with sine and cosine of theta, a 1 in position 3, 3. So it's a very simple matrix. So we have performed the actual rotation. Now we have to express things in the original frame. So I do the reverse operation. So the last product is C to the minus 1, but C is a rotation matrix. So this would be C transpose. By defining these three elementary operations, I have built the rotation matrix as the product of three. One elementary rotation and two other matrices, the direct and its inverse, for which I only know one row or column. The third column of C or the third row of C transpose. Okay? So let's do this computation. So here we are. C is defined by the three column vector NSR. Then the elementary rotation by an angle theta around the z-axis is this one. We have derived this last time together. And then we have the rows N transpose, S transpose, and R transpose. And now you see why we need this formula, which is slightly more general than this one, because in between there is no identity matrix, but there is some matrix. So I must add the contribution of the outer product of this column vector times this row vector, each multiplied by the scalar in the various position hk, ij, and so on. Okay, if I do this, and now I hope this is clear, I know that in position 1, 1, I have a cosine of theta, so this will multiply n transpose. So I have n transpose times cosine theta. Cosine theta is also in position 2, 2, so this scalar will multiply second column times second row, so S transpose. I have a 1 here in position 3, 3, so I will have the multiplication of R transpose, so third column times outer product with third row, multiplied by 1. And similarly, I have a sine of theta multiplying the first column times the second row and the symmetric one with a minus sign, and this is the result that I obtain. Okay? All those development were for understanding this simple equation. And in fact, I added some hints. How do I arrive here? Outer product of two vectors, dyadic form of a matrix, matrix product as products of dyads. Exactly what we have written on the blackboard. Now, am I done? No, unfortunately. While I know R, this is the data of the problem. I know theta, and so I know sine of theta and cosine of theta, but I still don't know S and N, the other two columns of the matrix C. And now those equations on the blackboard are helpful. In particular, look at this product. It's almost this one. In fact, I can isolate this part and bring the last term to the right-hand side, so I can replace this product by identity minus R transpose. Okay? So this is gone. Or better said, it can be expressed in terms of the data of the vector small r. This one is nothing else than the skew-symmetric version of the vector composed by R. Just check the rules that we have introduced last time, or that are in the previous slide, for a vector product, and you recognize that the results of this are combination, which are nothing else than the component Rx, Ry, and Rz of the vector product S and vector S, organized in a skew-symmetric matrix, so with a diagonal here, and then with change of sign. So here I will have plus Rz, in this position I will have minus Ry, and in this position I will have Rx. So as a result, I can rewrite this difference of two matrices, which are each of which is an outer product of vectors, as a skew-symmetric matrix built only with the data of our problem, in particular with the vector, unit vector R. So I'm done. Why? Because I have eliminated whatever I didn't know, and the result is R transpose plus identity minus R transpose times cosine of theta, this part, plus skew-symmetric matrix built with the unit vector R times sine of theta. And this solves the so-called direct problem. I give you a unit vector. I tell you all the world is rotating around this unit vectors by an angle theta. What is the rotation matrix associated? This is the rotation matrix associated. Okay? Now, if you look at this expression, it's quite simple to recognize. Let's look first at this. If you replace vector R with vector minus R, and instead of rotating by an angle theta, you're rotating by an angle minus theta around vector minus R, you obtain the same expression. Why? If you change the R, this is a product, minus minus is eliminated again. The skew-symmetric matrix S of minus R is minus S of R, but the angle theta has change of sign, and the sinus changes sign accordingly, so the two minus cancel here, while here the cosine is an even function, so cosine of theta is equal to cosine of minus theta, and you obtain the same result. So if I give you R and an angle theta, or minus R and an angle minus theta, you obtain the same, you're defining the same rotation. Okay? This means that this mapping between the axis angle notation, so unit vector small r and theta, and the rotation matrices is not injective. So you have two input data that goes to the same rotation matrix, which means also that if you try to solve the inverse problem, you will find typically two solutions, because two inputs goes into the same rotation matrix. Okay? This is another consequence. What is R transpose? It's the inverse of this rotation. So if I want to go back from the final orientation that I have obtained to the initial one, I just take the transpose of this matrix and rotate by minus theta around the same axis, and I obtain the same result. So this is also a consequence and also has an intuitive explanation in terms of geometry. So if we have a compact expression, but if we don't believe in this compact expression, we would like to make computation, and this is the horrible expression that you obtain just by expliciting this outer product, this matrix times cosine, this Q-symmetric matrix, and so on. So this is the final term. There are interesting things. For instance, do you know what is the trace of a matrix? The trace of a matrix is the sum of the element on the diagonal. Now, what is the trace of this matrix? Yes, what is the result of this sum? 1. It's 1? No? Well, cosine plus cosine plus cosine is 3 times cosine theta. This, you factor out 1 minus cosine theta, and you have rx squared plus ry squared plus rz squared, which makes 1, because this is a unit vector. So you have 3 cosine theta plus 1 minus cosine theta. So this is 1 plus 2 cosine theta. Okay? Which means also that if you sum the element of this diagonal matrix, you have some function which is not dependent on r. It's just dependent on theta. 1 plus 2 cosine theta. Okay? And there are other things that we can observe on this. So let's do a simple application of these results. For instance, let's take as unit vector one of the coordinate axes. For instance, the vector z0. What is its expression? Is 0, 0, 1 in frame 0. Okay. So we make a rotation of theta around this particular r vector, which is one of the coordinate axes, actually the z-axis. What do I expect to find? I'm expecting to find the elementary rotation matrix around the z-axis. Let's see if this general formula boils down to that simple expression. So R transpose, so this vector's time, this column vector time its transpose, it's a row, all zeros except a 1 here. This is identity minus this matrix, so I have 1, 1, 1 in diagonal minus this matrix. Those 1 remains, this is a 0, and this is multiplied by cosine of theta. And then the skew-symmetric matrix built with this vector. Remember, in this position you have minus rz, in this position you have here you have minus rz, xy minus rz. This is xz is ry, and then minus Rx, and then their opposite here. Okay, so here you have Rz, and this is the skew-symmetric matrix. Okay, times sine of theta. You multiply this, you sum, and you have the elementary rotation matrix. So that you can check, for instance, the other two elementary matrices that I left you as an exercise, Ry and Rx, same story. You can find that for the Ry, you will find a 1 here, but then the minus of the sinus function will be in the lower triangular part, just by construction. Okay? So this is a generalization of these elementary matrices to any axis R. This is another application. I don't know if you have ever seen or will ever encounter this so-called Rpdriguez formula, which is a formula that expresses the coordinate of a generic vector after the rotation by an angle theta around an axis R. And the Rpdriguez formula is this one, expressed in terms of vector product of the original vector v and the axis around which we are rotating. Again, v is the original one. Finally, the scalar product here, so it's the scalar product of r and v. So it's a classical vector-based expression. You have the vector product, your scalar product of vectors, and the result gives you the new coordinate of the rotated vector, whatever vector this was. Okay? Now we know that the new coordinate of a generic vector v, once we have done a rotation, and in particular here we are doing a generic rotation by an angle theta around the axis r, are given by the formula on top. And we have now an expression for the rotation matrix r theta small r, so we just apply the formula. So we have this formula applied to v, and now it's a matter only of reorganizing things. So we have RR transpose times v, and we have one component here and then a minus cosine here. Then we have identity times cosine times v, and this is the other term. And then we have a sine of theta, and then s of r times v can be rewritten in terms of the vector product r vector v. We are doing the reverse operation, and if you compare the two expressions, you obtain exactly the Rpdriguez formula. So this is just a proof, a simple proof of the Rpdriguez formula using the found expression of r of theta unit vector r. So what are the properties of this rotation matrix? In a sense, this is a generic rotation matrix, no? Because it's always, you can always define such an angle and a unit vector. So the first property is very simple. If you apply the rotation to the axis r around which you rotate, of course this is the only invariant vector. It will not change. So everything, all the world is rotating around r except r itself. So if you apply r to capital R, sorry for the confusion, so the matrix R you apply to a generic vector, this will rotate. Unless you're applying exactly to the vector r or to a scalar version, so a scaled version of this unit vector, this won't change. So this is a strong property. It's true, you can check it. Just use the expression of the rotation matrix capital R, apply to the small vector R, and you will find that nothing changes. And the interpretation is very obvious. Now, what can I say when I find a product of this kind? A matrix times a vector is equal to the vector itself or to a scaled version of this vector. What did I find with this equality? A a very important concept related to matrix and algebra. Maybe I can write it in a different way so that you can recognize it more easily. If you multiply a matrix A by some vector R, and if you find this one, then what can you say about X and about lambda? Lambda is an eigenvalue, and X is an eigenvector of matrix A. Okay? Now, what does this equation says? That unit vector R is an eigenvector, actually, of unitary norm. Eigenvector are defined up to a scaling factor, you remember, no? So it's an eigenvector of the rotation matrix, and the rotation matrix has an eigenvalue equal to what? What is the difference between this and that? So, again, the rotation matrix is a 3 by 3 matrix. How many eigenvalues do you have in a 3 by 3 matrix? 3. Are they real? We don't know. Maybe. Either they are all 3 real, because R is a matrix of real numbers. So either all the 3 eigenvalues are real, or one is real, and then you have a complex conjugate pair. There's no other possibilities. Okay? So associated to this eigenvector, there will be other eigenvector up to 3. The eigenvalue is 1. This is exactly this formula with lambda equal to 1. Okay, so one of the 3 eigenvalues is 1. The other 2 either are real or are a complex conjugate pair. Okay? But the main point is that the R-axis is invariant, and those are only consequences. Then this is already checked out. When R is one of the coordinate axes, the generic rotation matrix boils down to one of the elementary rotation matrix that we have introduced. This is the other property that is important, especially for what follows, that if we consider the map between all axis angles, so unit vectors in any direction and scalar value of theta, 2 rotation matrices, given by this expression, this is not an injective map. So we can cover any possible rotation, but we will have 2 elements from the domain that maps into the same element of the codomain. Okay, this means lack of injective property. Now, 2 more properties and some consequences. Forget about this. This property, that the determinant of a generic matrix, square matrix, is equal to the product of its eigenvalues, it's something that holds for all matrices. Okay? Not just for rotation matrices. What is true now is that our rotation matrix is of a special orthogonal group, so its determinant is +1. So we know that the product of the 3 eigenvalues of this matrix is equal to 1. Okay? There's another property which we have just found, namely that the trace of a generic matrix, not just the rotation matrix, this is always equal to the sum of the eigenvalues. Okay? Now, here I've written identities in brown hold for any matrix. You don't see the brown color here, but the brown is this one, and this one, and the trace and the determinant. So this external expression are equal for any matrix. Now inside we have done the computation for the rotation matrix. So if I compute the trace of our rotation matrix, is an exercise that we have just done together. This is 1 plus 2 cosine of theta. So the sum of the three eigenvalues is 1 plus 2 cosine theta, and the product of the three eigenvalues is 1, and one of the eigenvalues is 1. So we can conclude what are the other two eigenvalues. So from first property, we have that, let's say the first eigenvalue is 1. If we combine these two, so if we take this, we have that 1 plus 2 cosine theta is 1 plus the second plus the third eigenvalues. So we remove lambda 1 equal 1, so we write that lambda 2 plus lambda 3 is 2 cosine of theta. But we know also that the product, lambda 1, lambda 2, lambda 3, is equal to plus 1. Lambda 1 is 1, so we know that the product lambda 2 times lambda 3 is equal to 1. So we can replace lambda 3 in terms of lambda 2 or vice versa in this expression and multiply by this lambda, and we have a quadratic form in the unknown lambda, whose roots are the two missing eigenvalues. And if you solve for this, you find that the two eigenvalues, except for this term that should be on this part, are in fact almost always complex conjugate. Cosine theta plus imaginary identity sine theta and minus sine theta, which means that if you look at a generic rotation matrix around any axis R, and also for any R, the three eigenvalues are on the unitary axis, and on the unitary circle. One is always here, and the other two are placed symmetrically by an angle theta on the unitary circle. This is what this formula says. So you have a nice mapping. Any times you find a rotation matrix and you can extract the angle theta around some generic axis R, you know that that matrix will have this three eigenvalue. What do you do with this? Nothing at the moment, but later on these results may be useful. Okay? So now let's tackle for the first time an inverse problem. An inverse problem means that I have a bag with all possible rotation matrices. So all possible orthonormal matrix with determinant 1. It's a huge bag. I pick up one out of this bag, and this will be my data. It's red. So R is an orthonormal matrix with 9 numbers. Okay? Now my question is, can I find a vector R, a unit vector R, and some angle theta, such that when I rotate by this angle around that vector, I obtain the data, the rotation matrix R? So this is exactly the inverse problem that we have formulated before. Before we have given the unit vector R and theta, we have found the rotation matrix expression in terms of this data. Now we're doing the reverse. So I have to solve this matrix equation. R 9 numbers, special 9 numbers, because this should be an orthonormal matrix with determinant plus 1, but still 9 numbers. And these are an expression which have taken like this, or has the complete detail expression when we expand all this product. So we have 9 nonlinear equations in 4 unknown. The 3 components of R are x, ry, and rz, and the angle theta. In general, we don't know if we have a solution. And if somebody tells us that there is a solution, we don't have a direct method to apply. So we don't start saying, okay, we invert the matrix, we do something. We don't know. It's a nonlinear set of equations. Okay? Well, here we can solve it analytically in closed form, except for some singular cases. Okay? So the first thing that we can do is, remember, the trace of R, now it will be the sum of the 3 numbers on the diagonal of the data matrix R. Okay? So it's a number. So the sum of the 3 numbers on the diagonal, R11, R22, R33, we know that the trace is 1 plus 2 cosine theta. We know that this holds all the time. So we are tempted, pay attention, we are tempted to solve things as follows. I bring the 1 to the other side, I divide it by 2, so I have this number is equal to cosine of theta, so theta will be arc cosine of this number. This is okay, but it's not the best way for doing things, especially because you have values only in 0 pi, so you never get negative angles by doing so. And then when you're close to a value which is 0, then you lose numerical accuracy. And this is a second order aspect. But again, as I mentioned the other time, we care about computational efficiency and ways for not introducing non-robust computation. Okay? So this is good up to here, but solving for cosine is not good. Okay? Why? The other reason is that we are using only the 3 elements on the diagonal. So this is not exploring all the data in an efficient way. So we will do something slightly different. Well, we take again the data matrix R and we subtract its transpose. Since the result R minus R transpose is always a skew-symmetric matrix, correct? Why? If I take any matrix, so not just R, but if I have R minus R transpose and I transpose it, if I transpose this matrix, I obtain R transpose minus R transpose transpose, which is just R, which is minus R transpose. So the transpose of the matrix is the matrix itself with opposite signs. So this is a skew-symmetric matrix. It's the definition of skew-symmetric. If there was a plus here, that matrix would be symmetric. But there's a minus, so it's skew-symmetric. So if I do R minus R transpose, I obtain a skew-symmetric matrix. On the diagonal, I have zeros, by definition. And then I have differences of off-diagonal term of the original numerical matrix R. Okay? And if I do this in my expression of the rotation matrix R theta R, so I take this expression and I do this computation, I obtain this expression on the right. So I can factor out 2 times sine of theta, and then I find the skew-symmetric matrix with Rx, Ry, and Rz with the proper sign. So I look at this, and if I square these numbers, these 3 numbers, I square them, and then I sum them, I will get the same on this side. So I will get 2 sine of theta square, all square, and then rz squared plus ry squared plus rx squared, but this is 1. So I have an expression. I can isolate sine of theta. Remember that theta is unknown. And then extract the square root of this, and then divide by 2. And when I extract the square root, I take into account the fact that I may have a plus or a minus sign. Okay? So as a result, I have an expression for cosine of theta. It's a number. And then another expression for sine of theta actually are two numbers. This number with a plus, and then another number with a minus. Okay? So I take one of these two sine, and then I have two numbers. One represents the sine of theta, and the other represents the cosine of theta. So what I do is I take into account the sine of these two numbers, and I solve for theta with the arctangent function in 4 quadrants that takes value in all 4 quadrants of the 360 degrees. So this is the sine, is the first argument. This is the cosine, is the second argument. And then I get two solutions for theta. One when I take the plus sign, and one when I take the minus sign. So automatically I'm generating two solutions for theta. Okay? Now, if I look at this expression on top, the sum of the square of these differences may be 0 or not. If it's different from 0, that means that sine of theta is different from 0, then I can divide by sine of theta, which is this number here, and isolate rz, ry, and rx from our data. So I can find also the unit vector. The unit vector is 1 over 2 sine theta, where sine theta is this, and this is the numbers that I put, and make sure that this is certainly a unitary vector by construction. Okay? And again, since sine of theta is defined up to a sine, I will have two values. So if I take the plus sign here, I should use the plus sign here. So I take a theta and an r vector. If I take the minus sign here, I obtain minus that theta, and with the minus here, I obtain the minus of the original r vector. So I generate the two solutions. Since I know already that if I would have found only one solution, r unit vector and theta, by changing their sign, I would generate another solution, because this mapping was not surjective. So here you have an explicit form for the two solutions. Okay? Now, what happens if sine of theta is equal to 0? Which means that all these terms are equal to 0 in the original data. You cannot, sine of theta will be 0, so you cannot divide by 0 here. So this formula cannot be used. So if you write a MATLAB code for solving this inverse problem, you should make checks through the instruction to avoid that you have an overflow division by 0. Okay? Before seeing the singular case, let's take a look at the atan2 function, but because we will encounter it over again and again, okay, over and over. So this is the so-called arctangent function with output values in the 4 quadrants. It takes 2 input arguments. It makes the ratio of the first argument over the second argument like the y and x in the normal arctangent function, but then adds terms so that the result is located in the correct quadrant. Remember that, so if you have the idea behind is very simple. If you do the ratio of two numbers which represent the sine and the cosine of some angle, then these two numbers, so sine theta and cosine theta, here they are both positive. Here they are both negative. Here it's negative positive, here it's positive negative. Okay? Which means that if you just look at the two single numbers, you can allocate the solution in one of the four quadrants. If you just look at the ratio, then of course you cannot recognize if you are here or here, because this gives the same sign to the ratio. And similarly, if you're here or here. This is why you have to take into account the sign of each argument. The only situation where Atan 2 is not defined is when you have two objects as first and second argument that cannot represent sine and cosine of an angle. So which are even not scalable so that sine square plus cosine square is 1. When is this case? Is when the two arguments are 0. Then this function is undefined. Actually, this function is implemented in several programming languages. For instance, in C++, in MATLAB. In MATLAB, you have, pay attention, because if you call this function in MATLAB with 0, 0, the result is 0. Okay? Just if you look inside this function, you see that it's defined. Remember that any function at some singular point can be defined with the value that you prefer. If you enter there, you can replace 0 by 255. Why not? Okay? So this is not relevant. But pay attention that you should not use never this function with 0, 0, because otherwise something is wrong. You're not making the ratio of two numbers which represent sine and cosine of the same angle. So you have done a mistake before. Okay? So this is a very convenient function that will be used for many inverse problem solutions. Now let's look at the singular cases. So when sine of theta is equal to 0. So remember that if we go back to this expression, sine of theta, we don't know yet sine of theta, but we know its expression in terms of the data. Being 0 means that those terms are all simultaneously 0. Okay? So what we have two possible solutions. If theta is equal to 0, then there's no solution at all. Because, for instance, if you take as rotation matrix the identity, so all off diagonal are 0, so their difference square are 0, so it's exactly this situation. But the identity means that there is no rotation. So theta is equal to 0. But then you can rotate by no angle around any unitary axis. So R is not defined. The vector R is not defined. So the rotation matrix is not defined. The other situation is when theta is plus or minus pi, which means that sine of theta is 0, but then cosine of theta is not 1, but it's minus 1. So you go back to the expression, and you have your data here. This is the matrix of data. And on the right-hand side is the expression of the rotation matrix R theta unit vector R when sine of theta is 0, so you eliminate some term, and cosine of theta is minus 1. So you simplify things, and you have this expression. So you have a new system that you consider only in the singular case. Now, from here, since you take this outer product on the diagonal, will be Rx square, Ry square, Rz square. So on the diagonal, if you bring this identity to the other side, you have on the diagonal element 1 plus R11, 1 plus R22, and 1 plus R33 is equal to 2Rx squared, 2Ry squared, 2Rz squared. So you take the square root, divided by 2, and then take the square root, and bring with you the plus or minus sign. Okay? So remember that theta has been already found. It's either pi or minus pi, it's exactly the same thing. But now we have to detect what are the correct sign here. And in order to do this, you make sure that you consider the off-diagonal element in this identity, and you recognize that this product should be equal to R1 over 2, and so on and so on. So you consider this auxiliary equation just to select the right combination of plus or minus sign in this formula. Okay? At the end, you will find still two solutions, because you have found that you can rotate by pi over some r, or by minus pi over minus r. So you will find here, instead of having 6 possible combinations, only 2 combinations when you impose that this identity should also hold. Okay, these are only used for selecting the signs. For instance, here is an exercise. Given this R matrix, it's a rotation matrix. What should I check? I should check that this column is orthogonal to this columns, and this is true because this one points on the zeros and there are zeros here. That this column is orthogonal to this one, and there are minus, minus, plus, and here a minus of the same quantity. So again, this is orthogonal columns. Unitary vector, yes. This is 1 over 2 plus 1 over 2 is 1, same here. And then the determinant should be 1. There's a minus here, but then there's a minus here and minus there. So minus minus is plus, and if things are done correctly, this is really determinant plus 1. So this is a rotation matrix. This check should be done at the beginning of your program, because if somebody gives you a wrong R, then all the formulas makes no sense. So this is the first check that you should include in a robust programming of this solution. Okay, then look at the off-diagonal terms. This minus this is 0. This minus this is 0. This minus this is 0. So if we square and sum this, we obtain 0. So sine of theta is equal to 0. So this is exactly the singular case. Okay? But if I look at this term by the same formula, I will have that cosine of theta is minus 1, so I can use this expression for r. So I find that theta is plus or minus pi, but I still need to find the r vector. So if I see that r12 and r13 are zeros, so this gives me no information, except that Rx will be 0, probably. And then if I look at this element, or this element is the same, or maybe R23, this element, this is negative, so Ry and Rz should be of opposite sign. So the solution will be 0 here, because minus 1 plus 1, 0, so I don't care about this plus or minus. So R of x will be 0. And this is consistent also with this equation. R12 and R13 are 0, so here is Rx in common. And then from this, if I take the plus sign here, I should take the minus sign here. And when I take the minus sign here, I should take the plus sign. And these pairs give me two solutions, which are the two axis vector around which I should rotate by pi or minus pi to obtain this kind of rotation matrix. Full stop. Okay? So let's conclude with a single slide, which I mention here because you may later on or in other courses hear about quaternion. In this course, we are not using quaternion, but it's good to know that there are other representations of orientation. Up to now, we have seen rotation matrices, axis angle representation. But axis angle representation have this problem of inversion that may generate two solutions or singular cases. So in order to overcome this, people have introduced quaternion, especially in attitude control of satellites, where orientation is the most dominant aspect, not position. Position is in orbit, but then orienting the satellite is very important. So what are these quaternions, and why unit? Unit is the way in which they are built. So quaternion is a set of 4 elements. This is why the name quaternion. One scalar, let's call it eta, and one, it's a 3-dimensional vector. They are defined from the axis angle notation by cosine of the half of the angle theta, and this is the scalar eta, and then the unit vector r multiplied by sine of the half of the angle theta. Okay, so these are 4 numbers. If you take a form of norm of these 4 numbers, so the square of the first scalar and then the square norm of the vector constituting the other 3 elements of the quaternion, this gives 1. And this is thanks to this definition. So this qualifies the quaternion as unit quaternion. There are other quaternions that do not satisfy this condition. Again, if you take, and as expected, if you take 2 different representations of rotation in the axis angle, theta r and minus theta minus r. Remember that these are associated to the same rotation matrix. Okay? So there are 2 things for the same rotation matrix. Well, in quaternions, they generate the same quaternion. So this duplication disappears. And this is one of the reasons for using quaternion, and in particular unit quaternion. And then with this representation, you may do computation as you do with rotation matrix. You have only to introduce the suitable algebra. For instance, absence of rotation is a quaternion defined by no vector, so the 0 vector, and just the 1 here. This means that if you apply this quaternion, nothing changes. It's like with rotation matrix, the identity matrix. Only that rotation matrix are 9 numbers organized in an array 3 by 3. These are only 4 numbers organized in a quaternion structure. And then if you want to compose rotation, with rotation matrix you would do the product of rotation matrices. Okay? Here you have this special product. So if you have one rotation represented by quaternion Q1 and then another rotation represented by quaternion Q2, the final orientation that you get is the product of this quaternion, which is defined in this complex way with some scalar products, some vector products, scalar products, and so on. Okay? And I stop here because we won't use this again in the course, although if you're interested, you will find in the textbook some more details about this quaternion. Okay, let's stop here. Sorry for the start, which was a long one. I hope that my Mac doesn't leave me